Hello, everyone. Welcome to this next webinar. Today, we are lucky to have Dr. Thomas Souther discuss the topic of hybrid simulations of wind-assisted ships. Dr. Souther is a senior researcher at the SINTEF Ocean in the Department of Ship and Ocean Structures in Trondheim, Norway. He is also an associate professor at the Norwegian University of Science and Technology as part of the Marine Cybernetics Group. Today, he will be presenting an overview of his study on sail-assisted propulsion of ships using hybrid simulations. There's going to be a question and answer section at the end of the presentation, so please hold off on your questions until the end. Now, please welcome Dr. Souther.
Thanks, Edwin, for the introduction, and thanks to everyone for being here. So I know that most of you are not naval architects and not specialists in ocean engineering, but I hope this presentation will be interesting for you. The topic is wind-assisted propulsion, so I jumped straight into the reason for which we are looking at that. So the important number is that 3% of the greenhouse gas emissions come from the maritime transportation system. So it's quite a huge number. And if we want to be in line with the Paris Agreement, this has to be reduced. And the numbers we are looking at in terms of, or the factors that we are looking at in terms of reduction, they are quite huge. We talk about reducing by a factor 4 or 5 the emissions, and it's important to understand that if you do try to do an optimization of hull or a propulsion system, or try to improve your coatings with today's ship concept, you achieve, let's say, 5–10% emission cuts. That's already huge. So when we are looking at 75–85%, that's a very, very large effort that has to be done. There are many technologies to address this challenge. We can either try to reduce the energy demand, that's what you have in green here, or you can try to use a energy storage system or fuel that is less prone to generate greenhouse gases. I don't go into the details because we don't have that much time, but the one we are going to look at tonight is, or today, is sails. And that's an alternative, but it will probably, in the end, will be a combination of many of the systems that you can see on this list. So sails, let's say that it's a proven technology up to the 19th century. The ships were powered by sails, and the large amounts of cargo was transported by sails. Of course, you don't have the same guarantees as you have today in terms of delivery time and so on, but that's something that exists. In more modern times, you have the modern ships that get sail assistance, and here what you have on the screen is the Bukau. That's 1920. That's the first ship that is propelled with a Flettner rotor. So I will come back to that because that's the one we used in our study. But that's sail assistance in its first forms. So today we are looking at much more modern type of systems, but the rotor sail is still there. We are looking at kites on the right-hand side, but we also have wing sails that if some of you are interested in sailing, that's typically America's Cup type of sails. We have the classical soft sails that you have on most sailboats. And you also have rigid wings like these ones that exist. Many technologies, and very difficult to say at this stage which one is the best one in terms of course, propulsion force it provides, but also operational constraints it generates in terms of sail handling in a way. So if you look at this picture, you have different concepts, and you have actually different sail sizes that generate the same lift force that you can use to power your ship. And you see that they are quite diverse in terms of size and shape. And the way of quantifying performance of a sail is usually using a polar plot. And a polar plot is nothing else than the way of the lift that you can generate, or the power that you can generate in this case, as a function of the angle respect to the headwind. So let's say that this corresponds to the wind coming from kind of our headwind. This would be beam wind, wind from the side, and that would be following wind, wind from the aft of the ship, or from the aft of the sail. And you see directly that between rotor sails, wing sails, and kites, there are very large difference. For example, the kites can't really sail upwind. If some of you are kite surfing, you know that. So that's you could see that as a disadvantage. But on the other hand, a kite can be very easily stowed on deck of a ship when you have headwind, and in that case, it would not generate any spurious drag. So it's not really yet fully established which concept is the winning concept, and that's why we are looking at this problem. So what I said before, it was that we have the performance of a sail that is provided through these polar plots. Things get complicated when we put sails on a ship, because if you think about the sail, it will generate some propulsive force, but it will also generate a huge sideways force. If you've been sailing on a, let's say on a monohull, you know that when you are going upwind, beating, there is a large heel angle that comes from this side force. So the side force on the sails are huge, and that makes actually the ship drift a bit. So I don't go into the details about all the phenomena that are actually induced by this drift angle and this side force. But basically, the hull resistance changes, the forces on the appendages change, typically the rudders and the keels, the bilge keels, and so on. The interaction between the rudder and the propeller, which is something that is really optimized for a given type of ship, is changing. The propeller loads are different, so the machinery system will react differently than as if you didn't have any sail. The sail will cause quite a lot of damping in roll and pitch, and that will actually change something we call the added resistance in wave. It's not expected that you understand all these concepts, but that's an important part. And the bilge keels, which avoid rolling, will generate much more resistance when you have these sails. So it's a lot of phenomena that we need to investigate. And that's why we need experiments to assess the performance of a design, to be sure that we capture all these phenomena at this stage. Question, can we still perform classical propulsion experiments when we have sails on the deck? The answer is no. And the reason for that is twofold. You have first scale effects. And if you are familiar with the floating wind turbines problem, it's basically the same thing. There is a requirement, which is to run the experiments in fluid scaling due to the presence of waves, which are really important for the resistance and for the sea-keeping properties. So you have to use these scaling laws, fluid scaling. But for all the aerodynamics parts, that's Reynolds scaling. And the two of those are not really agreeing if you are not at scale 1. So at model scale, you can't get the two scaling regimes together. And if you don't use the right Reynolds number, which would be what we would do if we had a fully physical experiment, the loads on the sails would not be correct. So that's exactly the same issue that we faced with floating wind turbines. Interaction is also very difficult to scale correctly. between the sails and also between the sail and the substructure. The second challenge is that even if we could model the sails correctly, we would need an incoming wind field that would be that needs to be also representative of the full-scale wind field. In our ocean basin, where we test stationary structures, that's already a challenge. But when we look at a ship, we need to have we need to be in a towing tank, or we need to have actually a wind field that is kind of following the ship, and that's not feasible at this stage to have a good enough wind field. So the answer to that is hybrid simulation, or we can call it hybrid testing or cyber-physical testing. That's but basically it's to mix numerical substructures and physical substructures. How to do that? We say that the hull, the appendages, and the machinery are the physical substructure. Here we use this SINTEF Ocean bulk carrier, which is an open geometry, SOBC1, that's the code name, and which made it possible to publish results, or else the designers are a bit secretive about their performance. And the numerical substructure would be the sails. Okay. Here we have 4 virtual Flettner rotors that are on the deck. So you can't see them obviously, but we have 4 sails, 4 of such cylinders, rotating cylinders that are on the deck. I will come back to those. So a brief description of the experiments we've run. So basically the tests were performed in our towing tank. It's 260 meters long. Important, the model was free running. That's how we do propulsion tests. So it means that even if we are in a towing tank, the carriage that we are sitting on and that is moving is not towing the model. It's just following it. The propeller of this ship is powered control. So we have actually a full propeller arrangement and rudder arrangement, and the propeller is controlled to achieve given power by using simply a torque measurements and regulating the RPM. The autopilot controls the course of the ground, so basically it tells the ship to follow the center of the tank. So I'll come back to the hybrid simulation details later, but for applying or for computing the sail loads, we have a surrogate model that we'll come back to, and the loads are applied using a CDPR, cable-driven parallel robot, which is basically a set of 6 winches that are connected to this frame that you see up there. We'll see better pictures in a moment. And what we are looking at, what we record, is the ship speed. So we put a load, we input a power from the main machinery. The sails are here. We blow a virtual wind, and then we look at the wind speed, at the ship speed, sorry, the heading, the leeway, the heel angle, which is kind of the roll angle, and some more details that I will show later. This is a video of how it looked like in practice. So that's in Skull Motor. You see the frame up there. You don't really see the lines connected to the winches because they are really thin, but they're there. There are 6 of those. See some wake down there. We have another video, yes, in waves. It's exactly the same principle. You see a winch here and the second one there. And that's how it looked like in waves. Some details about the CDPR, how winches are, or all the actuators, where they are placed and so on. So if you, the blue lines here represent the the deck of the ship. So the frame that you saw it's mounted on the top of the deck, and the actuators are placed in a kind of star configuration, one above the other on each side. Here you see how they are placed. This is the lower one, and this is the upper one. Very similar to what we do for floating wind turbines, except that the frame here is in carbon fiber, while in the previous picture for the ship, it was in aluminum. And then we go to the numerical substructure. So of course we have to compute at each time step, or at each time instant, we need to have the drag and lift coefficients to get the lift, drag and lift forces that we integrate all over the sail, and that we sum for the 4 rotors to get the total load that the robot is going to apply on the ship. Just a small explanation about Flettner rotors. How do they work? So this is an example of a Flettner rotor. You see it from above, and assume that you have a wind coming from the side of the ship. Okay, that's the red arrows here. Assume that the rotor is spinning in this direction. You will have a larger velocity here than here, because there is friction, skin friction. So basically the velocity will be lower here than here. So you will have a suction force here, like in a wing, and you will have a pressure force here, and that will result in a lift force. So that's exactly how the Flettner rotor works, and it works. Some people are skeptical, but it actually works. And it's impossible to get, so yes, another thing is that the results, or the lift and drag coefficients, will depend on the spin ratio. And the spin ratio is simply the ratio between the velocity of the cylinder at this point and the incoming flow. So if you have the spin ratio, if you have some dimensions of the aspect ratio of your sail, and the end plate's diameter up there, you can get the lift and drag. You can get that through CFD. And of course, CFD is not an option in real time, and not in real-time model scale, which is square root of the scale faster than real-time full scale. So what we did was to use previously published CFD results that we found, made a surrogate model based on those, and used this surrogate model online, and it worked perfectly. So that's then it, of course, it boils down to the validity of these results, CFD results, but that's another topic. So that's how we compute the loads. Then look at the closed loop that is representing these tests. So if we start with the physical substructure, that's a vessel and the sensors that are embedded, accelerometers, gyros, motion capture, optical motion capture. From those, we go into an observer that computes the velocity, which is not measurable directly. So we compute the velocity, and we can evaluate this velocity at each slice of the rotor sail. And with our numerical substructure, we can get the lift and drag force that is generated and sum everything up. That's what we do here. I didn't, there are some tricks that we added. I will refer to the paper because I don't have time to go through that, but that's not really the key for the understanding the problem. Then once we have the load, so that's 5 components, we don't actuate the vertical load. That's so 2 forces and 3 moments. How should we pull on our cables to achieve that? That's the job of the allocation module that you see here. And then we send in 6 commanded forces to our winches, and the controller is ensuring that we get these forces, and the actuators are reacting, and then applying the tensions on the vessel, and so on. That's quite a classical setup. Results. Some results. So what I will show you here is the it's quite simple test. We varied the wind direction. So from 30 degrees off bow, so what we call close hold in sailing terminology, 250 degrees, which is broad reach, so the wind comes almost from behind. And we changed that by steps of 15 degrees. In addition to changing the wind direction, we changed the wind velocity, 10, 15, and 20 meters per second, which is approximately twice as much in knots, 20, 30, 40 knots. The ISO profile was used, so we actually had the real wind profile when we computed that's why we had slices to have the wind profile correctly integrated on the sail height. Results are presented in this also in this classical polar plots fashion. So you have the headwind represented by 0 here. That's closed hold, and then wind from the side, broad reach, and wind from behind. So there are different quantities, and for each one you have in black what we had for 10 meters per second, in blue 15 meters per second, and in red 20 meters per second. So I'll go through that quickly. We have the vessel speed typically. So if we did not have sails, the vessel would go approximately at 12 knots with the power that was provided by the main machinery. When we had sails, we could go up to 17 knots in 20 meters per second, but that was in a really nice angle, so wind coming slightly from the side. And if we go to angles that are a bit close to the bow, that would cause trouble. You see that the velocity is dropping below the value it had without the sail. So the rotor sail it's a major drawback. If you can't really fold it on deck, it will break you when the wind comes straight when you have headwind. The heel angle up to 3 degrees. So when we had the largest wind velocity, this run, the last run we didn't do, but it would be probably 3-4 degrees of heel, and that's very little. You could see it on deck probably, you can feel it on deck, but it's not a problem, and that's because the ship is quite massive. Trim is so the heel was the kind of the roll, and the trim is the pitch, and that's negligible, 0.1, 0.2 degrees, unaffected by the wind. Drift angle, so the boat would kind of drift sideways with 3.5 degrees. That starts to become a problem when you do long routes. Interestingly, you see the thrust, the fraction of the thrust that comes from the sails, and you see that you can reach quite good values of up to 60% in these conditions. More problematic, the rudder angle. So that's the last one, last plot. You see that when you have large wind velocities and you are in closed hole, you could have actually up to 20 degrees of rudder angle. So the ship is kind of needs to compensate the sideways force from the sail by using the rudder, and that's a lot of forces that will break the ship. That's not an optimal way of using the rudder. And we tried to do some maneuvering tests, typically zigzag tests, that's called, and we didn't succeed because that was the ship was not maneuvering well enough, so we would basically hit the wall of the towing tank. Much more in the paper. I will give you the reference afterwards if you are interested. Conclusion. So for the sail-assisted propulsion, the hybrid simulation now enables us today to obtain quantitative and reliable estimates of the benefits of a wind assistance propulsion system in calm water. We are still in calm water now. We haven't looked at the results in waves. We can very easily change the sail arrangement on deck. That's very handy when that's in the numerical substructure. And of course, as usual, when you do experiments, you discover unexpected effects. And here, that was the loss of maneuvering capabilities. That was much worse than what we would have expected. And that's the reason for that is that this bulk carrier was designed for not having sails, so it's a retrofit. And the rudder was optimized to reduce resistance. And it was quite small, and that's too small for when you have sails. I'm already quite late, so the future plans, I will let you read that offline. I can just mention, so the details are in a paper that you can read if you like. It's open access. And just kind of zooming out, and we have sail-assisted propulsion coming as an application that follows floating wind turbines, as you see here, and estimation of nonlinear hydrodynamic loads, something that we have worked on recently also. So it's very many applications of these methods in marine aerodynamics. Very interesting. And really, the fact that we have hybrid simulation, it helps us a lot with the infrastructure issues. Here, the wind, for example, that we can't model correctly, the scaling laws issues that we have here, Reynolds and Fruit scaling. We can run the test automatically, changing the wind, for example, test by test, very efficiently. And what we are looking at now in projects we have with other partners in Europe, for example, Aarhus University in Denmark, we are working a lot on optimal experimental design using hybrid simulation. Sorry for the small delay, but happy to be answering questions if you have some. Thank you.
Thank you, Doctor, for your presentation. Now the floor is open for questions. So if you have any question, you can unmute your microphone or you can drop your question in the chat.
Yes, I have a question. Thank you very much. That was a very cool, very nice presentation, Thomas. I'm sorry I connected late, so maybe you did mention this, but maybe I didn't hear it. Can you elaborate a little bit more about the type of actuators that you use for this type of tests? Thank you.
Yes, so the actuators they are exactly the same ones as we use for floating wind turbines. So basically, it's homemade actuators. So they are doing force control, but we are using position-controlled motors, very off-the-shelf motors, with a compliance which is homemade to achieve force control. So if you drop me an email, I can send you some references on the details about that.
Okay, and you connect them to your physical part, and then you identify them just like any other actuator. You get your frequency response and how to do the tracking. In this case, the force tracking controller. That's how you manage the control part.
Yes. So the controller, you let me know if I go into great details, but the controller is split into 3 parts, let's say. You have one part which is force tracking, one part which is disturbance rejection, because when you saw the ship in waves, for example, you see that if you want to apply a constant force and the ship moves, you need to have a system to. And the last part so these two are feed forwards, and the last part is a feedback control. So basically, it's just like what the other two couldn't make, this last one should take it, but it's not. This one should not work too much.
Okay.
Yes.
It's really cool. I'm going to take a look at the paper and maybe shoot you an email if I have any further questions. Thanks a lot.
Don't hesitate to do that. Thanks.
Can I ask you one question? 2 questions. I am Oh Sang-won from University of Toronto. And can you hear me, by the way?
Yes.
Okay. Thanks a lot for a very interesting presentation. I have, in fact, 2 questions. The first question is, about the rotor. So for the ship to propel, the rotor should rotate. And what is the source of energy for the rotation? Do they need to apply any external power, like using any engine in a ship, or it just rotates using a wind power as well?
Yes, so to answer your question, it's the first question. It's you're right. You need to have some machinery down there at the to make that to rotate. Of course, the energy that you use to do that is much less than the one that you get from the sails. So that's definitely a good question. So you have a rotating part here.
Okay.
Yes.
Then my second question is about the surrogate model representing the relationship between wind and the lift force and drag force, etc. And I assume that the ship will rock back and forth based on the lateral force as well. So the wind speed will change and the wind attack angle will change as the ship moves forward and it shakes back and forth. So is this surrogate model compiled such that it can take into account changes of wind direction while it is keep moving?
Yes. So the surrogate model is just basically this CD and CL, so lift and drag coefficients, as a function of different parameters. And indeed, when the wind, for example, when the ship accelerates, the apparent wind velocity will change. Okay.
Yep.
So it means that these coefficients change, and that's integrated into the surrogate model. So everything is solved in is updated in real time.
Okay, thank you.
That being said, the main limitation of this model is that it doesn't account for any unsteadiness in the flow. So there are steady CFD simulations that we use in an unsteady simulation, which is basically you use the quasi-static type of approach. It remains to be seen if it's good enough or not. That's definitely something that it's still an open question, but that's the best we have as of today.
Sure, thank you.
I have a question. I was able to read some of the paper, and one of the sections says that for the aerodynamic model that was used, the wind shear sail hull cell interactions were neglected. I was wondering if you could try to explain a little bit more why they were neglected and how they affected the results, maybe.
Yes. So why they were neglected? Basically, is because when these authors did these simulations, they didn't. I mean, the simulations are made with a cylinder that is probably between two wall boundary conditions. The advantage of that is that you can basically you try to use these coefficients for any type of ship because you don't model what's below. The drawback with that is that it will be wrong for all types of ship because it's not a wall boundary condition that you have below that. But it's basically just a first approximation of the coefficients that you would get by that. Just to be sure that you see. Oh, sorry, that was there. Yes, so basically we talk about sail-to-sail interaction. One of the rules is to try to put the sails such rotor sails, so not like the ones presented here, but the one that we discussed earlier, to put them at a distance to each other, which is equal to approximately the sail height. And you will get interaction when you have a very sharp angles compared to the wind, so the almost wind to the coming from the bow. But when you get wind from the side, which is where they are the most efficient, then you will limit the interaction between the sails. But again, that's first approximation. In our computations, we just used results that were steady, so that's what I answered earlier, but also for sails that were in an infinite fluid. But of course, that's also wrong, because we need to have to include this interaction with other sails and with the substructure. First approximation, so it's definitely something to improve there. Was
Okay,
it clear?
thank you.
Yes.
Yeah, thank you. Is there any other questions?
If I may, I have one more quick question. So in this real-time hybrid simulation, what is the update rate of the controller? So how often do you run the numerical analysis, and how often do you update the command to the force control of winches?
The observers and actually the whole loop runs at 200 hertz in model scale or in our world scale. So it's I know that for structural engineers it's extremely slow, but we have systems that are much less stiff than what you are used to. So 200 hertz is it's actually we are working at the scale of, especially here what I showed, the results I showed, it was really for steady problems. So it's not really there is very, very little requirements on the controller efficiency, but when we have waves, for example, typically the wave period in the tank is 1 second, which is much larger than what you would get for earthquakes, for example. And the ship motions are also at the order of the second. So it's so basically it's 200 hertz, and 200 hertz is adequate for this problem.
I see. So the model itself is essentially satisfying static force equilibrium. So there is no potential dynamic instability issue. Is my understanding correct?
You mean the numerical model of the sails?
Yes.
Or
Yes.
You mean the whole closed loop system?
In fact, what I meant was the numerical model first.
Yes,
But
so the numerical model is really basically providing a force as a function of a speed or reduced numbers computed from the speed.
I see.
So there is no really instability there, but you could. I'm trying to think about what you are after, what you are thinking about, because we can get some instabilities in other type of applications, but not in this one. It's a very nice one because it's a steady. At least the results I presented here were like steady tests.
In structural hybrid simulation, depending on the lag in the controller, and because we have dynamic system in the numerical model, it sometimes depending on the lag or numerical integration scheme, we may see stability issue during the simulation. But in this problem specifically, I guess what you are saying is that the numerical model predict force, which is modeling of the wind and rotor interaction, and the physical model, in fact, represent the structure and the wave. And we are not modeling wave, but structure floating in the water.
You're right. You're right. So the instabilities that come from in the closed loop system, including everything, the actuators, and so on. such instabilities can occur if you have too much lag and so on. And that's something that we have observed in our lab. I think anyone who runs hybrid simulations and said that he has not experienced instabilities would probably lie. But not with this problem, because we had very little dynamic excitation that could trigger such instabilities. So it's and enough damping. But that's definitely a problem that is that we know of, and we definitely are aware of. But that's not for this application.
Sure, thank you.
Thanks.
Is there any other question? Okay, so if there is no more questions, I think we can finish this webinar. Thank you again, Dr. Soller, for your presentation, for your answers and time. We look forward to have you again with us in future events.
Thanks for the invitation. It's nice to have good questions, and you can. I dropped a lot of the content on the propulsion analysis and so on that I think you are not that interested in, but if you are, you can just have a look at this one.
Thank you.
Thank you.
Other than that, thank you all for coming, and have a great day.
Bye-bye.